We'll now take a look at the list interface that's given to us in the collection. And we're going to show how to implement this interface using both arrays and linked lists. The list collection is actually specified by the list interface, and this is given in the java.util package. Now, this interface does extend the collection interface, which means it has all of the methods that are in the collection interface and then some additional methods that the list interface provides. So let's take a look at just a subset of what this interface has. So here's some code that gives us a couple of the methods that would be given in the list interface. So we see at the heading that it is called list. It's an interface, and it does inherit from the collection interface. And then we still have the any type in the angle brackets, because when we actually create objects of the implemented class, we can specify if we want a list of integers and doubles and so forth. So we see we have a couple of methods, a get method, a set method. So these are very similar to the get and set type methods that we use in our classes in CS121. We have an add method, a remove method, and then we also have a list iterator method. And like I said, there are other methods in this interface, but these are the ones that we're going to be looking at in this class. We'll start by talking about the get and set methods. And these methods just allow the client to be able to access an item or change an item, depending which method you call, at a specified position in the list. So we would pass a value to say, get the item at this spot or set an item at this spot. And this is given by the index. So here we're going to call it IDX as the index or the position that we want to actually look at for our list. And for the index here, it's actually going to be very similar to how we deal with arrays. Index 0 is going to be the front of the list, and then the size -1 is going to be the last item in the list. And then size, well, not only is it going to tell us how many items are currently in the list, but it would also represent the position where a newly added item can be placed. So if we have to add a new item, we're going to add it at the end, and we can use this size value to say, this is the place where we're going to add the next item in the list. The add method simply allows us to add a new element to our list. So we do have the value of the item as a parameter, but we can also specify exactly where in the list we want to add it. So we do that by using the index parameter, the IDX. Now, as far as wherever we add it, any items that come afterwards would have to be pushed over one position to the left. Now, we've talked before about what happens when we add items in arrays and linked lists, but from a notation perspective, the position values of the subsequent items would have to be incremented by 1. Now, just to give an example here, if we did an add at position 0, that means we're going to add the item at the very beginning of the list. And likewise, if we were to do an add at position size, then that means we're going to add the item at the end of the list. And of course, we could add the item somewhere in between 0 and size. We also have the standard remove method, which just simply removes a specific value. So we pass a parameter of type any type, and this just means that we're going to find that particular item. If it's there, we're going to remove it. If it's not there, then it's going to be up to the programmer on how that's actually handled. But we also have an overloaded version of remove, and this passes the specific index as a parameter. So here, instead of trying to find a specific item to remove, we're going to say remove the item at this position, and then we just remove it and then close up the list accordingly. Finally, the list interface does specify the list iterator method. And I should mention that this does produce a more complicated iterator than what we've seen so far with iterators. In fact, we're going to talk more about the list iterator interface a little bit later on. So we're not going to talk about now other than it is one of the methods that was contained in the list interface. We now need to look at how we're going to actually implement this interface. And there are two popular approaches to this. We have the approach that's called array list, which just simply means we're going to use an array for implementing our list abstract data type. and then we could use a linked list approach. So we have the linked list approach. With the array list approach, it actually gives us a growable array implementation of our list. So if we need to increase the capacity of our list, we can do so. And what's nice about using the array list implementation is that the calls to get and set take constant time. And this is because we can directly access the elements in the array. The problem with this implementation is that if we try to insert or remove items, they're going to take O of n time because we have to go through the entire list to move things around. So they are a bit more expensive. With the linked list approach, it actually provides a doubly linked list implementation for the list abstract data type. And what's nice about this approach is that whenever we're inserting or even removing existing items, they are very cheap. Now, this is assuming that we know where those changes are going to take place. If we don't know where they are, that's a problem. But what this does mean is that adding and removing things from the front of the list are constant time operations. In fact, the linked list does provide different methods such as add first, remove first, add last, remove last, get first, and get last to allow us to efficiently add, remove, and access the items at both ends of the list. So if we have to do stuff with the ends of the list, that's going to be done very efficiently. The problem with using this implementation is that the linked list is not easily indexable. We do not have indices for each node in the list. That means things like calling the get method to find a specific node can be very expensive unless they're really close to one of the ends of the list. Let's compare some of the methods that operate on a list. We'll start by constructing a list by adding items at the end of the list. So here's some code that would do that for us. So this is a public static void method. We'll call this makeList1. And we're going to pass in a list of integers. And then n is going to be the number of items in the list. Now this is a very simple method because really we're just adding 0, 1, 2, 3 all the way to 9 in here, but that's, or not 9, but whatever n-1 is, but that's perfectly fine. But we first call list.clear, so that clears the contents of the list. So think of it kind of like initializing the list. And then we have a simple for loop where for each iteration of the loop, we're going to call list.add I. So we're going to add I to the end of the list. Now this particular construction approach is going to take O of n time, regardless of whether we use array list or linked list. And that's just because each call to the add method is going to take constant time because we're just adding it to the end of the list. So regardless of whether you use an array or a linked list, adding something to the end is going to take constant time. Since there are n things we're adding, that's going to take O of n time. Now let's suppose we construct the list by adding items at the front of the list instead of the end. So we can have some code that does that. So here we'll have a method that's called makeList2. We're still passing our list of integers, and n will be the number of elements we're going to add. We're still going to clear the list, and we still have a for loop where we have this I that goes from 0 up to and including n-1. Now take a look at the add method call that we have right here. So we're using a different version of the add method. This is saying that the first parameter is telling us where we're going to add that, and then the second parameter is going to tell us what we're going to add. So we're always adding I at position 0. So we're always just adding it to the front of the list, and that's how we construct our list. Now, if we use the linked list approach, this is going to take O of n time. But for an array list, this is going to take O of n squared. So why do we have this difference in the two approaches? Well, in both cases, we have O of n calls to the add method. Our for loop has O of n iterations. The difference is the running time of the body of the loop. For a linked list, it takes O of 1 time to add an item to the front. We just change a couple things with our next and previous reference variables. So adding stuff to the front takes constant time. For an array list, though, that's going to take O of n time to add to the front, because if we add something to the front of the list, we have to shove everything else over one spot in the array. So that's why we get an O of n squared time. That's why the array list approach takes O of n squared time.